know Steve dropped.
Okay, so I will start with just a simple explanation. Assertion delay, it's just asserting something. Like the pandemic is really annoying. Is an assertion, right? It's just saying something is true. So an assertion is going from 0 to 1. And so it's how long it takes in order for something to do that. A de-assertion delay is the opposite when you go from 1 to 0. These times can be different because you could have a circuit with different drive strengths, right? So you could have a circuit
So that's the same thing as propagation delay?
It is not. It is linked,
Okay.
but it is slightly different. So say we have this circuit, and this is V out. The two things that can happen is either I turn the circuit on, right? If I go from a 0 to a 1 here at the input, when it's a 0, that means this is off. V0 is pulled high through this resistor. When I turn this on, it shorts V0 to ground, and V out is 0, right? So it's inverting, right? 0 here means 1 here. This is just an inverter. But you'll notice that these are not mirrored components. So this guy, when he's on, has some resistance. But let's say this is a 1 kilo ohm resistor, which is a reasonable amount, because you kind of want this to be big, because otherwise it leaks power, right? So there is some issue with that, because if you have the switch on, this is connected, and power flows through here, so any time that the V out is 0, I have what we would call static power consumption, because the current has to flow from VCC to ground constantly if this is 0, because this isn't a switch as well. So I want this to be kind of big. Now let's say that on my switch, we have this term called R on, which is the resistance for the switch being on. And say the R on is 10 ohms. So what that means is that when I pull to 0, it can do very quickly, because the bigger the resistance, the harder it is to make that transition. So this pulls to 0 very easily compared to pulling it back up to 1. So the de-assertion delay is actually going to be lower than the assertion delay. I need to make sure I said that correctly, because inverters are awful. Because an inverter, the assertion delay is going from 0 to 1 at the input, which means the output is doing 1 to 0, right? But this is still the assertion delay. Even the output is de-asserting, the input is being asserted. So we care about what's happening at the input. So the de-assertion delay is 1 to 0 at the input, which is 0 to 1 at the output. And so they can be different. Now the propagation delay is the longer of these two. And it's not just necessarily one gate, right? So I could have something that so this circuit has several things going on. Each gate has an assertion and de-assertion delay. But the overall circuit also has an assertion and de-assertion delay. And the longest of those is the propagation delay through the circuit. Is that more clear? Yeah. Okay. Let me grab a drink. I've been talking a lot. Okay. So next week, a week from today, we have an exam. Monday is scheduled to be a review. I will, okay. So I have gotten unforeseenly busy. I'm not going to grade all the homeworks. What I will do is I will get answer keys out to all the homeworks. So you at least have something to compare to. Before the weekend. That's my goal. I will get it to you even before Monday. That's the goal. It may not happen till Monday. I will try to be better than that because I really want you guys to succeed at this. So chapter 8 is the last thing on this exam. Don't get too confused because we're not doing all of chapter 7. So we've done like the first half of chapter 7, which is K-maps. We're going to chapter 8, and then the second half of chapter 7 will be on the next part. So for K-maps, you only need to know how to do 4 variables. You don't need to look at a section that's called map entered variables. Chapter 8 is pretty interesting, if a little bit light. They title it the design process and binary arithmetic, but it really should be titled something more like using binary arithmetic to understand the design process. That's what we're going to do. We're going to go through both binary arithmetic and designing things. So the design process is fairly intuitive, right? You start by getting the requirements. What that means is, what does the system need to do? And most of the time, that's either going to come from a customer or your boss or your professor, right? They're going to say, I need you to design a circuit that does X. I don't like this book's design process. We'll stick with it because what it has, because the get the requirements is really a 2-step process by itself. Because there's get what the customer is asking for, and then there's the turn that into engineering lingo. Because a non-engineer, a customer isn't going to come to you and say, I need something with a circuit that does X and has a propagation delay of less than 300 milliseconds. They're not going to do that. They're going to come to you and say, I'm designing an automatic braking system for a car, and I need it to work if the car is driving 25 miles per hour and a child runs out in front of it 30 feet ahead. Right? Those are different things. That turns into propagation delay between the detection and the braking, but they're not going to give it to you that way. So that's really part of the design process. But the main thing is get the requirements. That was the book simplifies it down to. The next is understand the concept. What is it doing? And that's not just, it doesn't mean just break, right? In that example that I use, it could be, how does the algorithm detect that there is a child or something, right? You have to understand some sort of more mathematical concept, which we turn into an algorithm, which is step 3, which is understand the algorithm that we've kind of started understanding and using, or you have to develop it. Because there might be an existing solution, or you might have to come up with something new. More often than not, something exists, right? And the way to kind of look at it when you get in a professional field, you may run into this if you get into like an R&D industry job, is a rule of thumb-ish is academia is about 10 years ahead of industry. This isn't true in every field, but in lots of fields this is true. And so as an R&D engineer, a lot of times what you'll do is you'll go and look into academic papers and see if you can turn what some people have done there into a useful product. And then you may have to buy it from that school or whoever holds the patent, but that's really just kind of how it works, is you start out with that. And then the nice thing with most algorithms is it can be divided down into little subsets. As an entry-level engineer, you're just going to give some piece of an algorithm. Someone over you is going to say, like, I have this algorithm, and I need you to design me a 4-bit adder to go into my algorithm. You're going to go, okay. And then as you work through your career, you'll move higher and higher up until you're coming up with the algorithms. Or not, or you'll end up, in management. There's lots of paths in engineering, it's kind of fun. Then you'll implement it, and you'll test in a term what we call bottom up. So the design process is usually what we call top down, where you come up with a big idea, and then you start breaking up into parts in order to design it. That's top down design. Test is always bottom up. So you're going to have some little block that you were assigned or you assigned someone else, and you're going to test that block. And if that block works in the test, you can assume, if you did your test well, that'll keep working when you plug it into a bigger system. And then you'll test that bigger system using lots of little blocks. And you'll take that bigger system, plug it into a bigger system, and test it, right? So like your cell phone, for example, has tons and tons of things going on. Someone didn't sit down and start writing the operating system from scratch, right? There were blocks to it. There are building blocks in something like an operating system or an FPGA system. So, we're going to use an example of an adder. We want to add arithmetic together. Now, the book likes to point out that if a customer ever came to you and said, I need you to design me an adder, you would just pick up a part and go, here you go, right? If you need an adder in an FPGA system, which is programmable logic, which we'll get to later in the semester, you would, instead of handing them apart, you would use what we call an IP core, which is intellectual property core, which Xilinx, Altera, all the major FPGA designers have them, and you just drag and drop a little block, and there's an adder for you, right? Because this is a problem that everybody's run into. But we're going to pretend that we can't do that, right? Say we're cheapskates and we went for some really horrible FPGA, and we have to design our own adder. So we need to get the requirements. So the requirements are, and they're listed on page something or other near figure 8-2. It's like the third page. I wish I had page numbers, but I don't. You're going to have two 4-bit inputs representing binary numbers A and B. So we're going to try and add two 4-bit numbers together, right? Then we're going to have a 5-bit output. Because if I add two 4-bit numbers together, I could potentially get a 5-bit output. It goes on, the outputs are active high, they're TTL levels, so that tells us what voltage they need to be. It has output drive and propagation delay requirements. Let's not worry about those just yet. So, binary arithmetic. The next step is understand the concept. How do we add things together? Well, we're not elementary schoolers, so we have at least some idea. But binary is different, right? Simpler though, because we can only do one bit. One, 0, 1, 1. Okay, we can do this, right? Well, this is 0. This is 1, that's 1, that's 2. Wait, no, not, right? What is it? Yeah. So we have an issue because now we've got that spillover, right? So we added 1 bit so we can get 2 bits. Just like if you had 2 bits, you could get 3 bits. Two 2-bit numbers, you get 3 bits. What we do though instead is we call this 0 with a carry. That's just like when you add, I don't know, 17 plus 5, and we do this thing where we go, okay, 7 plus 5 is going to be, there's a 2 here, and there's a 1 up here, and now I get 22, right? That number overhead, that's the carry. So we run into a more interesting problem. What happens if I add 1 and 1? Let me see if I can actually come up with a more intelligent example. I swear I wrote one down. Oh, well, I guess I didn't. Okay, so 1 and 1 is 0 with the carry, right? Now we come to our next problem. What is this? Well, it's 1 with the carry. So those are all the things that we can add, and it stays true regardless of the number of bits we are adding together. So we go and do something silly, and we want to add together 1, 1, 0. Oops, there's one more 1 here. And 1, 0, 1, 1. Now, this isn't that hard, right? 1, 0 with a carry. Now I have 1 and 1, that's still 0 with a carry, right? And now I have 1 with a carry. Or they asked us to have a 5-bit output, we'll just take the carry over. So it turns out our carry, we call this a carry out, can be used as our largest, our MSB. And it will never add to anything, so we can just use it directly because we're adding 4 bits and this is a 5-bit slot. Similarly, this may be the higher order bits of a larger number, and you may have a carry in, right? That is possible to have a carry in and a carry out. And that's the nice thing. This is the fundamental idea of what we call a ripple carry adder, which one of the two? Like ripple carry adder, a ripple adder is for short. And what they're just saying is it ripples along adding them all up. And we can build this into a circuit pretty easily. And look at how to do that. If you are at all unsure, there is an example 8.1 and example 8.2 that you can add things together with the right answer displayed for you. I don't think you guys need me to add more than this, or do you? Does anybody want me to do more addition of binary numbers? I didn't think so. Okay. So now we're going to do something which we know we're designing. We're creating some combinational logic. That's what we're doing, right? There's combinational or sequential that I've alluded to. But we're still designing combinational logic. How many inputs is our combinational logic going to have? We're adding A and B, and each of these are 4 bits. Therefore, we have 8 inputs. Okay. There's a bit of an issue, is if I wanted to draw out the truth table for this, right? We talked about truth tables. How many lines of truth table is that? How do we figure that out?
2 to the 8.
Yeah, 2 to the 8 lines. You could do that, but that sounds kind of awful, right? So what we do instead is we take the fact that this is an algorithm, and most algorithms are do this and repeat and do this and repeat and right, blah, blah, blah. And we know that there's only 5 different things that we can add, right? 0, 0, 0, 1, 1, 0, 1, 1, or 1, and then we have a carry or not. So what happens if we design just a 1-bit adder and then just start sticking them together, right? So that's where we come into this idea of half adders and full adders. Half adders are basically a full adder, but they just don't have a carry in, right? There's no option to carry anything in. So if I'm looking at this, let's go ahead and design, well, from a conceptual level. We're going to start top down conceptually. If I have one adder, and we'll call this guy the half, and it adds A0 and B0. And we're going to have a full adder over here. So each of these are going to have an A and a B input. They're going to have a carry in, a carry out, and a sum, right? So this is all the same, C out. This does not have a C in, it just has the A and B. So let's say I design each of these, which we will get to. They're not that hard, but I want to hook them up in such a way that they are now 2 bits, Well, it's unsurprising that you might take the carry out of one and plug it into the carry in of another, right? And then this carry out can go on and so forth. But this sum out is just going to be the result at the bottom, right? And the carry out is if I'm putting a 1 out. So we add 1, 1 together. Sum out, so then S0 is equal to 0. And C out is equal to 1. Then this guy, let's say I have another 1, 1 with a carry in. What is this one? 1. And then A and B are 1 and 1. So we still have a carry out is 1. So now I can see that my number is 1, 1, 0. Feel good? Do you believe me when I say I can just string more and more of these together? Yes. Right? So that's how we build an n-bit ripple adder. We can just make this as big as we need to. Now this is actually pretty slow. This is an awful adder, but they're easy to understand. Because it's just, I build a half adder or a full adder where I just set the carry into 0, right? There's no even real reason to design a half adder without that. Then I design a full adder, and then I just copy and paste it a million times. The problem is, what concept did we recently learn that might cause us an issue if we wanted to go quick? Yeah. Propagation delay, right? Because you're going to have the propagation delay of this plus this plus this plus. So if I had a 32-bit adder, I'm going to have 32 times the propagation delay of this. So there are smarter algorithms that are implemented today, but this is a good place to start. Okay, so now we've understood a high-level concept, right? We understand how to add numbers together. We understand how to subdivide that into little problems. We understand how we're going to put those back together to solve the big problem. So let's dive deeper in. We started big, we're going deeper and deeper. It's top down, right? How do you design a full adder?
For the 5-bit one, we need at least 5 of them, right? So since that displays 5 of them,
So a full adder just means that it has an A, a B, and an S output with a carry in and carry out.
okay.
So the way we design almost anything starts, what is this?
Truth table.
The truth table. What are our inputs?
A and B,
And
the carry in.
yep, C in. So there's a couple ways that you'll see me do this, and I always start doing it the hard way. You can write out each of these numbers in order, or you can recognize that there's going to be a pattern, which is 0, 1, 0, 1, 0, 1, right? And then this is 0, 1, 1, 0, 0, 1, 1. And this is 0, 0, 1, 1, 1, 1. Right? That's actually a quick way to do it. I always forget to do it. 8 rows, because there's 2 to the 3 inputs, is 8. Then we have 2 outputs, which I'm not sure if you guys have seen yet. C out and sum. Okay. And now I need the truth tables for each of these, which are going to go ahead and we're going to say 0, 0. Well, I guess I should walk you guys through, right? A and B added together. The sum is obviously 0, and there's no carry. 0 with a carry in, there's going to be no carry out, but the sum is 1, right? And so I can go start looking through this. This sum is going to be 1. I need to write this a little bit smaller just so it fits. Sum is 1, no carry. And you can go and solve one row at a time, or you can start looking for patterns, because patterns can sometimes speed up the filling in, where I can start going, if there's two of these, I know I'm going to have a carry and a 0. And if there's one, I know it's a 1 and a 0. And I can just kind of flow through and fill this whole thing out. I think I'm going to rewrite this whole thing just a little bit higher, if that's okay with everyone, so I don't get this hodgepodge mess. And then I'm going to switch this around because I don't like the way it was written. Okay. Then just to keep this quick, the sum is 0. Sorry, sum. And carry out is going to be 0. Making sure I did this correctly. Okay, I think that's right. Yeah.
Everybody knows the left side of the board's out of view on your.
Thank you. Okay, fortunately, I didn't miss too much. If you're watching online, all I was talking about is the call out that A plus B is 4 bits, 4 bits, 8 inputs, 2 to the 8, blah, blah, blah. You can rewind. That's the magic of videos. Okay, I have a truth table. Now, we can turn this into logic, right? We know how to do that. What tool did we recently learn to design optimally logic?
K-maps.
K-maps, beautifully. So let's start with a K-map. How many K-maps do I need for this particular problem? 2. I need 1 for each output. So let's start off with a K-map for sum. It's only a 3-variable K-map. What number goes here? 1, 1. Remember, because we need logic adjacency. Now let's do some filling in. What's important to us is probably the ones, right, the min terms, which is where it runs. So we're looking at sum, and we're going to say something like, well, if A and B, C is 0, 0, 0, it is 0, right? If it is 0, 0, 1, we've got 1. If we've got 0, 1, 0, we get 1. And now I've started to see the pattern, right? But we got to skip over this one. So we go 0, 1, 1, 0, 1, 0, 0, 1. Right, so I just read top to bottom on that, remembering to go 1, 2, 3, 4, 5, 6, 7, 8. And you can even label it that way. You could draw, like, you'll sometimes see this notation, in fact, where it's 1, 2, 3, 4, 5, 6, 7, 8. They also might be 0 indexed, so you might start at 0. I like 0 indexing. I don't know what the book does, so I just want to bring both to your attention. Another way of writing this, remember, notation is important, is you can say something like F is equal to the sum of, shoot, I forget the book terms that the book uses, but you do something like sum of min. Some people just assume sum is the min term. I think that's what the book does. And then my min terms are.
It has a lowercase.
Oh, it has a little m. Okay, thank you. Yeah, so notation can vary quite a bit. And I'm using two different books that use different notation between the two classes I'm teaching. And then I just look at the ones that are. So it's important to know if you're 0 or 1 index. I've written this as 1 index. Let's switch it to 0 in our heads just to make things complicated. So 2 becomes a 1, right? So let's clear things up because we all like 0 indexing. So now I have 1, 2, 7, 4, and 7. Right? So the function is the sum of the min terms 1, 2, 4, and 7. We need to solve what that is. I'm just reminding you guys of notation, right? Repeating is good. Now we taught you minimization tricks with K-maps. Is there anything useful that we can do to minimize this one? Not really. We've got a 1 here, a 1 here, a 1 here, and a 1 here. So how many terms am I going to have? 4 terms. And each terms of those is going to have how many inputs on it? 3. So we're going to end up with lack of useful markers here is frustrating. Okay, are we good if I erase what this originally looks like, just so I have some room? Figures in the book, so you can always go relook. F is equal to, well, we want to look for things that, well, aren't changing when we do big circles, but these are individual circles, so nothing is changing, right? So we're just going to start looking at what these terms are. So I know I have 4 terms of each of A, B, C. So this is how I'll start. Because I know that's the direction I'm going. And now I can just start looking to see which ones have bars over them. So in my first term, everything but a C has a bar, right? Do you get that? So A and B bar, because A and B are zeros. C is 1, so it's a 1. Term 2, A is a 0, B is a 1, C is a 0. Do we get where I'm getting these bars from? Is anybody confused? Because this is important. All good? Okay. 1, 1, 1, nothing is barred on that one. And then finally, term 4 is going to be A is 1, B is 0, C is 0. So the only thing that doesn't get a bar is A, right? If I ever do something wrong, I will make mistakes, right? I'm not perfect at this, and I don't practice this. So I just kind of go up here and do it. So if I make mistakes, call me out. I'm not embarrassed to screw up, to be honest. So that's our equation. We can't really simplify that. This is an optimal. Now, what is it optimizing again for?
Speed.
Propagation delay, yeah. This is a minimal propagation delay circuit. It is also fairly easy to turn into universal gates, which we will get to. That's actually a really fun chapter, is design from these equations. Okay, the next one. Do you guys want me to go through filling the K-map, or do you want me just to skip to the completed K-map? Hands for filling in the K-map. No one cares? Awesome, cool. Okay, so now we're gonna get ourselves, and this is sum. Which I guess we could just do it this way if we're smarter than I am. Sum is equal to that. Can the screen see this green?
Yeah,
Okay.
it's a little light, but that's good.
Shoot, did I screw this one up? Because I'm wondering if I flipped sum and see out. No, never mind. Sorry. The way the book did this.
That one was some, yeah.
Yeah, the way the book has this label had me confused, but
Yeah.
we're okay. Now we can do some minimization, right? We're not just stuck. The minimization here is a little bit weird, but it helps hammer home an idea that I have had juniors in my later class not remember. So this is an obvious one, this is a good one, and that's a good one. Overlapping is okay. In fact, we'll find out later that overlapping is good. Hopefully, I mean, I just jumped straight to it. Hopefully you all know how to draw a circle around just pairs, right? Remembering that you are limited to circling 2 to the n of them in rows or squares. They need to all be logically adjacent. Diagonals are not viable because that's not logically adjacent. And L shapes are not okay either. Also, 3 is not a 2 to the n option. Okay. So, out of this, we have C out equal to and this is C in. Cool. Please do put them in alphabetical order when you start labeling these equations. So don't do like C in A, do A, then C in. That makes it way easier for me to grade. Dirty little secret, if I'm grading your homework and it's easy to grade, I get to go fast, which means I'm less likely to catch any errors you might have made and you get better scores. So the cleaner your work is, the less likely you are to make a mistake, even if there's a mistake in that clean work. If it's messy, I tend to have to dig through it and puzzle out what you've done. That's more for homework than exams. I'm actually pretty detailed on the exam grading. Sorry, now I have to gather my thoughts and remember what we're doing. Okay, are we okay if I erase the truth table at this point? Now we need to design a circuit off of this. We have 2 equations. And we know what the plus signs means and we know what multiplication means, right? So this is important. If I have circled ones, I am developing a sum of products. I'm going to have 2 tiers of gates, and we start with the output gate. We always start with the last gate. If I have circled ones, that last gate is always an OR gate. Similarly, if I have circled zeros, which you can do, but that turns it into a product of sums expression, so it would look something like that, right? Product of sums. Then that would mean that my output gate is an AND gate. But we usually circles the ones because we like minterms more for some reason. So the OR gate then feeds into, well, in this case, if we're doing sum, 1, 2, 3, 4, AND gates. And each AND gate has 3 terms. Does that step make sense? Is this, I can't remember, we talked about this? If not, that's okay. So then we would start filling in the terms, like I would just go ABC, ABC, so on and so forth, and then go back and puzzle in what gets the bar, and so on and so forth. There is one more step from this, which they don't teach you yet, so we'll wait on that. This is how you design that gate. Do you guys think you could fill in the remaining two AND gates? Do you think you could then start from nothing and do C out? Anyone not think they could? Okay, this is important, but I'm going to trust you. There is in figure 8.7 the final result of this. The output then, in this case, is going to be sum. Yes?
We start with the inputs A and B, but in the process we have another input that will be C.
So in this C, this is all Cn.
Yes, but the original equation is A plus B in 4 bits. So,
Well, it's A, B, and Cn, right? It's just 3 inputs.
but because we redesigned it. I mean,
I'm sorry, I'm not following, because we still only have 3 inputs. It's just whether they're inverted or not. This?
Yes.
Oh, this is actually really interesting. What you're looking at, each of these A's is 4 bits. Oh, sorry, no, 1 bit. Then we just do this 4 times. We're building just one full adder, so it's a 1-bit adder. So you just repeat this a whole bunch of times to get, we'll get to that. That's actually the next step. So now we've designed a circuit. I'm skipping a few steps, right? And inside of this box, and this is how we do VHDL, is there is a sum block of logic and a C out block of logic. And each of those will feed to the output of this black box. And then we can go back to that other figure right? So all we built is we built this. Well, actually, we built this one. So it only has 3 inputs, A, B, C, N.
And C was created from A, B, or
From this previous AB. But we don't care where it came from, we just care that it's there. Right, because we're building only this block. And the logic only knows what these blocks are. This block has no idea what it's connected to. It's not a smart block, it's just the logic does what the logic does. So these exist inside of this block. And then we can just repeat this as many times as we need to start creating this ripple carry effect. And that's the next step of the design process that they're going to talk about, is sticking them together. Actually, we're skipping one. We don't want to stick them together yet. What we do want to do is take this logic that we built, this black box, and we create something that we call a test bench. We will eventually learn how to design a test bench. What a test bench does is it takes this black box and it sits and throws inputs at it. You tell it what inputs to throw at it, and then it reports what those outputs are. And you know what the inputs or the output should be based on the input, so then you can do some evaluation, say, this is working as a 1-bit full adder. And if this works as a 1-bit full adder, then when I start sticking them together, it should work as an n-bit ripple adder. So individual box, full adder. Stick them together, sorry, individual box, full adder, stick them together, ripple adder. We'll probably talk about some other forms of adders, maybe, if we have time. So then the last, recall, we test from the bottom up. So we test an individual one, then we'll stick them together and test them there, right? Test from the bottom up, design from the top down. VHDL, which is a language you'll learn later in this class for programming hardware, lends itself really well to top-down design. Any other questions on this before I move into the next design example? Okay, I'm going to erase everything. I'm going to take a drink, and then we'll move on to a 2's complement adder. So, the 2's complement adder is not that different, actually. I should probably look at the time to make sure we're doing okay. 11:20, this ends at 11:45. Okay, we're okay. What do? We get the requirements. Now, these ones are going to be a little bit different. We're still going to have an A and a B. They're still going to be 4 bits. But our output only needs to be 4 bits. And our final carry out which I will label as C out comma N, so it's an N bit, right? We could do this as 4, but our final carry out is just an indicator for overflow. So it's not worried about what the last number is, it's just worried about if we tried to add too big of numbers together. So it's going to be useful between -8 and 7, pretty sure. And the outputs are active high, is what we want to specify. We've done the dot low, right? So if you remember, if we did all of that previous design and I ended up with some, if I wanted to turn that into an active low, right, all I have to do is go circle, right? Nice and easy. Okay. So the next thing, we have the requirements. This is what we're given. This is what it wants. Oh wait, not. Yeah, sorry. We're good. There's a third example that I'm not sure we'll get to that is actually a subtractor. Pretty interesting, but you may have to go through that on your own time. So I like this book. It's kind of funny. It goes on and it says the mathematics of why this one works is beyond the scope of this class. That's fine. So this happens. There's actually, I like it. I do like it. I'm not being facetious. I really do like it because there is, in the real world, you will pick up a design and you'll look at something like you'll look at an academic paper and they'll have extensive proof that it works. And you'll look at that math and go, I don't want to learn that math. You don't have to. As long as it works, it works. I don't care how it works, right? Someone else proved that it works. So let's use it without understanding it. We're engineers, we're not physicists. Okay, so if we start thinking them as 2's complement. And we have these numbers. And we start adding things together like we would normally, right? We don't do anything special. Well, 0 plus 1 is 1. 1 plus 1 is a 0 and a carry. 1 and 1, well, we have the same thing, 0 and a carry. 1, 1, 1 is, well, it's a 1 with a carry, right? Now the question is, we don't care what the carry is, right? What we do care about is this number correct? What is this number?
9.
Well, kind of. What is this number? Because remembering that this is, so right here we're 0 or 1, 2, 4, minus 8. So we're minus 8 plus 4, minus 4, plus 2 is minus 2. So this is minus 2. Similarly, minus 8, minus 6, minus 5. We should get minus 7. 8 plus 1 is minus 7. So this worked. Now there's something that's interesting about this, and that we know that it worked. And this is me just telling you that this is how the algorithm works, and you don't need to understand why. Because if your last carry in matches your final carry out, it's good. That's all. So that's our rough algorithm. And so we can tell that we need the same thing, right? We already have a ripple adder. And we're just going to build this guy up as a ripple adder. But instead of using the carry out for something, we're going to add one logical expression, right? There's only one thing. So you're going to have a third thing in our thing. You're going to have a sum block, but instead of a carry out on the last guy, you're going to have an overflow, OVF. That overflow is actually really simple logic, right? Because the only thing that I care about is CN3, because we're going to be 0 indexed, so it's 4 bits, so the third one, right? And Cout 3, right? That's the only two things that I'm comparing, is the carry in to this adder and the carry out of that full adder. And then the logic, well, I want them to match. If they don't match, I have a problem. But the issue is, this is not, if they do match, then we have not overflow, right? So really, in order to get overflow, what's that gate?
Exclusive OR.
Yeah, just an XOR. So we just throw one more gate as an XOR, and then we otherwise ignore the carry out, and now you have yourself a 2's complement adder. There are examples of this. I did example 8. Nope, I didn't. Examples 8.3 and 8.4 if you want to look at some of the 2's complement addition. Yeah.
So would you just put the overflow one on the last, as the last gate of it?
Exactly.
So you do the simple adder beforehand.
Yeah, full adder. You do full adder, full adder, full adder,
Then end on.
then you use a full adder, but then you just attach an XOR to the carry out and carry in. Actually, don't even know if they point. I think they do it in an even harder way, which is really funny. The book shows you a different way to solve the logic. So that they show that overflow is equal to carry in, carry out. Yeah, C1 is carry in, C2 is carry out of the last one. But unless I did something completely insane, that's just an XOR, which, based on my experience, that looks like an XOR. Anytime I see something like this, I start doing suspicious that's either an XOR or an XNOR. And then you can just draw the truth table to find out. The issue is the reason you might want to implement it this way, right? Because this is going to be two ands and an or. This will be a fun sneak peek. You don't need to know this yet, I don't think, unless we've covered it and I don't remember. Right, so this is how you'd execute that. It's because I have two AND gates connected together by an OR gate. Not very difficult. XORs are not universal gates. They're not used as universal gates. This circuit is very easy to turn into just XORs. Sorry, not just XORs, just NAND gates. Because, have we done that? Have we done gate conversion in this class? I really don't remember. No. So the general idea is this is a NAND gate. Oh, wait. Right? But NAND gates have an alternate drawing. This is also equivalent to that. Well, doing this is really easy because what happens if I invert an inverted signal? I end up with the original signal, right? So what happens if I add an invert here, invert here, invert here, invert there, right? So I invert, we're equal. What's this? NAND gate. What's this? A NAND gate. Ta-da! I've made a universal gate circuit. Super easy. I feel like we did start covering that, didn't we?
Yeah.
So that's how you do the conversion. Just a nice refresher. I'll look back on it. I think there's a homework that had some questions. If you've done it in the lab, it's fair game for the exam. Labs are fair game for exams. Remember that. Okay, let me check the time because I think we're running out. No, we have 15 minutes. Excellent. So our next section I guess I should point out, so what you're learning in this class is the fundamentals of digital logic, building circuits up. You'll eventually start learning VHDL and build into a microprocessor, actually. Understanding VHDL is how you program hardware. The next step for a lot of FPGA designers, so FPGAs are programmable logic, you'll use them in 3610. I will admit 3610 is a hard class, but it is probably also the single most valuable class that you can take as far as career payout goes. That being said, what the next step is after you know VHDL, so you'll pretty understand that after 2700 and 3610, the next step is understanding DSP algorithms, right? Because that's what you do with an FPGA, is you start implementing algorithms that are like facial recognition or automatic braking or various other things you see all over the place. So you do need to understand VHDL and algorithms. Hopefully by the end of this, you have a good basis for VHDL, and we'll move on to, in 3610, you'll get good meat behind it and build some actually useful projects that will go on your resume. Anyways, the point is what we did, right, was just an algorithm. You'll do lots of algorithms. We're gonna stick to simple ones for now. And in this case, our next algorithm is a 4-bit full subtractor. The difference is we're going to stick with A and B, and we're going to A minus B. But the thing that we're going to change is instead of a carry out and carry in, we're going to start worrying about a borrow in. Right, so we have the idea of borrowing in our subtraction, right? So if you do something like 17 minus 9, well, I can't do 7 minus 9, right? Because they teach you column by column when you're in elementary school. So I have to borrow from this 1, so I make that a 0, I give it a 1, now it's 17 minus 9. Now, it's obnoxious to learn it that way, but that's what we do, right? Well, fortunately for us, binary doesn't have 10 digits, right? It doesn't have 10 values per column. It has 1, right? It's 1 or not. So borrowing functions a little bit differently in binary and is actually simpler. So what we can look at actually do that last. Well, 0 minus 0 is 0. 1 minus 0 is still 1. 1 minus 1 is 0. 0 minus 1 is, well, here's where we have to start borrowing. But all we have to do is, interestingly, it's 1 and to borrow. So I borrowed something in, and I subtracted. So I had a 1, 0. And I subtracted 1 from 1, 0, and I get 1, right? That's all that's saying, is I get that borrow. So let's do a bigger number. Bigger subtraction. Okay. 0 minus 1, as we just did, is a 1, and I need to borrow. Okay, this causes a little bit of a problem, because I have a 1 and a minus 1, which would be a 0. But this 1 and that 1 cancel out, so I'm really back to 0 minus 1. So I get 1 and to borrow, right? Now I get minus 1, positive 1, we're back to 0. Okay, we've now fixed the problem of that borrowing that we had, and we can do 1 minus 0 is 1. A little bit more complicated one. This one is not in the book. If I have zero minus 1, 1 and a borrow. 1 minus 1 is 0 minus 1, 1 and a borrow. That's a repeat, right? 1 and a borrow. But now I have a new problem. I have minus 1, minus 1. Now I'm at minus 2. What goes here? A 0 and a borrow. And then minus 1 and a 1 is 0. There are examples 8.5, 8.6, and 8.7 that you can go through and make sure that you understand subtraction. It'd be fun. I will probably throw something like this on there that would hopefully be like 3 points, right? But if you don't know how to subtract with a borrow, you might get a little confused. But it's subtraction, so I hope it's pretty much 3 points. Okay, so the algorithm then is saying that subtraction is performed on each column. The borrows are propagated rather than carries, and the first column may need to handle a borrow in. So then, time is an issue. Let's skip ahead a little bit just to make sure. So it's just going to throw a big math equation at you. But the general idea is that if you add 2 to the number of bits that you have, so 2 to the n, to this, then you are doing the same thing as complementing the number. That's a little bit of math trickery that is outside of the scope of this. But you can say something like this is true. So this mess of an equation, I think there's a bit of a, I think there might actually be a question that I have you do on the homework to understand this. But this is a way that converts subtraction of b into just more or less addition with the 2 to the n. And I strongly recommend you start reading so right after example 8.7 in the book is where you want to start reading and understand the algorithm. Because it's going to do as good a job as I am actually in this, because it's magic, right? This is not a math class, and we don't want to go through this deep proof of this. But what the point is, this does, is once you start to understand the algorithms, you can start using this to build a full subtractor with a ripple adder. They're actually the same thing with more or less no difference. And so if I were to do something, drawing it up, don't worry, I'm not going to throw the ripple subtractor on the exam. I'm not going to torture you with that. I can see your worried faces. I will spare you that much. It's just not helpful at this point in time. Maybe at a later exam, once we've learned some more on the algorithm side of things. Well, here's your logic. It's the same thing, right? The only difference is you don't have the luxury of using the half adder in the first circuit because you may need to borrow in. And that borrow in is going to tell you something useful, which is that if the negative if it ends up being a negative number in that first column. The truth table, there's on figure 8-15, probably is the most straightforward way of understanding that, since we speak truth table, right? We understand that. This is one of the cases of you don't have to understand the math to understand its usefulness. And that's what I want you to take away with, is that you can use a ripple adder to build a subtractor, whether or not you understand the mathematics of the thing. It will take you through the simplification of the K-map on the full subtractor because it is a little bit different. Let me read the homework really quick to see if there's anything I need to explain more in depth to answer this. Oh, that's fun. I'm going to take that one out. It's kind of useless. It's fun, but with the exam coming. Does anyone have this homework pulled up by chance, fully assigned? I'm about to end the class. It's about time, yeah. But I want to look up the